Hey, welcome back to the stream. I think it'll just be me today, but I want to come in and check what's going on. Come into the live. It says I'm live. And I can hear myself. Cool. All right, so I'm streaming. I wanted to come back to these identifying equations of motion and this free body diagram, kind of our three-step, well, like two main steps: free body diagram, kinetic diagram, then equation of motion. But step zero, I call it step zero because it's kind of the fundamental part, and it's what we did in module 2, just identifying what's moving, like what is free to move and what can't move. So I wanted to go through this process. The more you see it, the more it helps. So I know I'm repeating myself as we go through each of these problems, but as you see this kind of over and over, it starts to make sense. So when I'm looking at this red balloon and I'm just thinking about like what is the free motion of this, like what affects how this balloon can move. We brought up some people brought up some good ideas of like, well, there could be drag. Like maybe if this thing is trying to move up and to the right, maybe there is a drag here. Maybe there is like some total like force of the wind. Maybe something's blowing the balloon. All of those are kind of like things that are forcing the balloon to do one thing or another. But if I just want to know, like, if the balloon is just floating in air and someone releases it, like the string is at an angle like this and it gets released, what's going to happen? And if there's no like noticeable drag, then the balloon should move up, it should rotate, and because it'll be moving fast, it'll continue past that point to some other point, and then because now it's somewhere else, it's going to swing back. So if I'm trying to figure out what is that motion, how do I describe that? The first question is how many degrees of freedom, and we correctly identified there's 1 degree of freedom. And that comes from the fact that the balloon is at some xy coordinate, but we're saying that that xy coordinate has to be along this circle of like length L. That the circle has a radius of L because that's the length of our string. So L squared, not plus, L squared. I'm flipping back and forth, sorry about that. L squared equals x squared plus y squared. This is one constraint on those 2 degrees of freedom. And I could have chosen r and theta. I could have chosen like 2 other independent coordinates, but overall, if I'm trying to say this is where the balloon is, I need to describe it with 2 coordinates, but those coordinates are bound together somehow. And since I know that they're fixed, so 2 minus 1 is now 1 degree of freedom, which means I'm only looking for one equation of motion. And that's why I call it step 0. I need to identify that in order to figure out what am I describing in the motion of this. Now from there, since I know there's only 1 degree of freedom, I can add all these extra forces, but at the end of the day, they're only going to be affecting 1 degree of freedom. So if I have a force pointing this way, I have a force pointing that way, at the end of the day, everything has to add up to some MA in that direction, along that A theta direction. That is my sum of the forces has to equal that. And I'm just getting rid of these. And let's go through this and just like erase all this, start from scratch. So I'm looking for one equation of motion. I know these are the forces involved. So if I look at what are the forces in the R direction, I've got this, that's my angle theta. So this is also my angle theta. So I've got a negative mg cosine theta, and then is that right? Yeah, and then a positive 2 mg cosine theta. This is my like mg term, and this is my fb term. And then a minus t, because I'm taking this whole thing and just trying to figure out like what are the components along that ER direction. So my mg term is moving along that cosine part, and then that FB is also that cosine, but in the positive direction. It's going along ER. And then tension is always in that radial direction. And then the sum of the forces in that theta direction are going to be a positive mg. And again, I want to figure out, at least it helps me to think about where these unit vectors are pointing. So my ER is always directly away. E theta is always pointing in the direction of how my angle increases. You can do it different ways, but if you want to stick to this method, it's a nice like tried and true kind of method. Let me put these in different colors so they don't look like forces. Like that. And get back into black. So positive mg sine theta and a minus 2 mg sine theta. And then tension does not act along that direction. So since I have that mg and a 2 mg, they all kind of add up into one. And I'll just put this as MAR that way and MA theta that way. Okay, cool. So I could take, if I want, I could take out this M, just cross it out here and say this is T over M, and then cross it out from every term here. So now I've got AR is mg cosine theta minus T over, oh wait, why did I do that? G cosine theta. And then A theta is going to be negative G sine theta. And this AR, I keep looking it up, but here I'll take a minute to actually talk through how this works. So let's say I have an X coordinate and a Y coordinate. If I want to describe this position P, the position of P is R times ER, where this is my like ER unit vector. Theta is the angle that describes that unit vector. So then E theta is going to be pointing up this way. So the only component, the only unit vector that I need to describe position is ER, because it's always in that ER direction. So let's note derive AR and A theta. All right, so now I want to figure out what is velocity of P. So it's moving somewhere. Let's say this is my velocity. It can have some change in R, it can have some change in theta, but overall doing something. And then we'll also say, and it's got some like acceleration. So velocity of P is going to be the change in the R, so dr dt times ER plus R times the change in ER dt. So d-ER dt. It's like, but it's a unit vector. How am I supposed to get the derivative of a unit vector? Well, I can write it out in my Cartesian coordinates. I could say ER is cosine theta I plus sine theta j. And now instead of looking at like how does this unit vector change, like how do I take a derivative of it, I have two functions. Derivative of I and derivative of j are both going to be 0. So really I'm just taking d dt. So when I do d dt of this, it's just taking the dot here and the dot here. So this ends up being a theta dot sine theta, so negative, plus a theta dot cosine theta along that j, or this is theta dot times negative sine theta along the I plus cosine theta along the j. And this part is kind of cool because negative sine theta, so moving over this amount by sine theta and moving up that amount, cosine theta, is describing E theta. So d dt of ER is theta dot E theta. What? So when you take a derivative of these unit vectors, you end up rotating them by 90 degrees, at least if you take d theta of this unit vector. All right, so now I've got velocity of that point P is r dot ER plus r theta dot E theta. Pretty cool. Now that acceleration of point P is, I have to do chain rule 5 times now, or kind of 3 times. I have to do it for this and this, this, and that. So kind of like 5 terms that are gonna pop out of here. So r double dot ER plus R, and I already figured out der dt is E theta times theta dot, so an r dot theta dot in that E theta direction. Now I can move over here and I end up with an r dot, a theta dot in that E theta direction, so there's 2 of them. And then plus an r theta double dot along that E theta direction. And then finally I'm taking that the derivative of E theta, which is going to give me a negative ER times theta dot. So I end up with a minus r theta dot squared along that ER direction. So the acceleration, and all I did was say that this thing has velocity and it has acceleration. I didn't define that there are any constraints on it. So if something's moving in 2 dimensions, these definitions work every time. We can always describe velocity and acceleration with these terms. So collecting all the ERs and all the E thetas, I end up with r double dot minus r theta dot squared along that ER and r theta double dot plus 2 r dot theta dot along that E theta direction. Cool. Now coming back to our red balloon. Let's grab just this equation that we were working on before. Paste it down here. And then we're going to take those 2 terms, delete them. delete. So I'm going to take this r double dot minus r theta dot squared, put it over here, and then r theta double dot plus 2 r dot and theta dot, put it right there. I know that r, so remember we have our constraint, it's only 1 degree of freedom. R equals L, r dot equals 0, r double dot equals also 0. So anywhere I see an r double dot or an r dot, it's all gone. That has to be 0. And they end up with, and really I could end up with 3 equations, because you can always take some of the forces in the x and the y, or r and theta, like you can always take some of the forces in 2 independent ways. And then I could do some of the moments for a 3rd equation. It's gonna end up being the same as this last equation. And if we got another minute, I'll show us how to do that too. But we can always use some of the forces in one direction, 90 degrees to that, some of the forces in that direction, and then also a sum of the moments if we want to get every kinetic equation that we can out of our free body diagram. But if we only have 1 degree of freedom, then we should only end up with 1 equation of motion, like one thing describing how this thing moves. So in equation 1 and equation 2, equation 1 is all first order derivatives. So I have this like theta dot term, and then this theta term. And then I also have this T, an unknown constraint force. And that's important because T is whatever it needs to be. So if this thing is moving fast, T is very high. If this thing is moving very slow and cosine of theta is 0, so if it's at like 90 degrees, the tension is 0. Like there is no tension when this thing is on the ground and it's not moving. It'll start to float up and then tension will increase as it's moving, but this equation 1 is a constraint force equation. So it's just telling us that T is G, I guess I should put an M in there, right? mg cosine theta plus mr theta dot squared. So I need to know what the balloon is doing in order to describe tension. I can't do the opposite. I guess if I knew the tension, then maybe I would know something about theta and theta dot, but I would need one of them. I need something. I can't just, this is not a solvable differential equation because T is an unknown variable and theta dot are both functions of time. So I can't solve that, but it is a constraint force equation. Number 2, I can say theta double dot is negative G over R times sine of theta. That's a very solvable equation. In its current form, it's a little hard to solve because we have this nonlinear sine theta. As engineers, we love to linearize it. So we can say let theta be much less than 1. Now theta double dot is negative G over, oh, I'm calling it R. Yeah, I'll leave it as R because I already have this thing up here. Sine theta becomes theta. Now I basically have a spring that is gravity driven. So theta, oh, I didn't mean to put a dot. Theta of T is something, some kind of cosine times root G over R times T plus something times sine of root G over R times T. So when theta is much less than 1, then that is my equation of motion. But this is my like general EOM, linear EOM. Linear is in the solutions are not straight lines, but as in like every time we have a theta double dot, or a theta dot, it's always a constant times that value. And the nice part is we always end up with sines, cosines, and exponential functions to describe those. All right, so then let's do one more, because I said we could. Yeah, so I have, well, let me just sum these up. Overall, I have mg pointing up that way. And that's at this distance, at some distance r. And then I have like that tension acting this way for this balloon, the free body diagram. So if I look at some of the moments around this point O, it's going to be R cross mg along that j direction. So it's that positive, this positive j direction. And then tension, I already know that tension creates no moment because it's going straight through the origin. So that's my sum of the moments. This is R ER crossed with mg. And what I could do is say that it's the same, like, let's see. So this is theta. Mg cosine theta along that ER, and then minus sine theta along that E theta direction. So taking that J term, and I could do it either way. I could define J in terms of that ER and E theta, or find the two components, but somehow if I'm taking a cross product, it helps to put them all into one coordinate system. Otherwise, cross products get a little tricky if you're trying to do cross product of things that are not orthogonal. ER cross ER is 0. ER cross E theta is positive K. And if you do E theta cross ER, then you get a negative K. So now I end up with R mg, or well, I guess a negative RMG sine theta in the K direction. Okay, cool. But what is sum of the moments equal to? Sum of the moments, it's not equal to MA. It's equal to the change in the angular momentum around point O, which is the angular momentum is R cross MV, or ddt of RER crossed with M times, and remember we just described the velocity. This is R times, well, we can say R dot along that ER plus R theta dot along that E theta. And taking this cross product, the ER and ER both cancel out, and we end up with d dt of R m R squared times theta dot, or m R squared theta double dot. So taking both of these together, d dt of HO equals sum of the moments around O is m R squared theta double dot equals negative mg sine theta, well, mgr sine theta, or theta double dot negative g over r sine theta. So because we only have that 1 degree of freedom and our system only has those 2 degrees of freedom, we end up rederiving the same equation of motion. At least for pendulums, you'll always get this same result. That yeah, nothing new comes out of that sum of the moments. If you have like rigid body problems, then sometimes it's a little different. But I wanted to show, really, that's our 3 when we're saying like FBD equals K, our kinetic diagram. Some of the forces along like E1, some of the forces is along some E2, and then some of the moments around some origin is going to be that change in angular momentum around that same origin. So we always have those 3 equations that we can deal with. If you're in 3-dimensional motion, then you actually have 6 equations because you have 3 components of force and 3 components of moments. Here we'll stick to 2 dimensions, at least for now. The other one, it's just an extra D if you add more dimensions. Cool, but I thought this would be a nice like review of kind of where we left off last week, and then when we get back together on Wednesday, we'll jump into next homework problem and like finish up. Cool, thanks for joining.